Hello, everyone. I'm Wei Xiao from Intel compiler team. Today, let's talk about enabling hardware-based PGO for both Windows and Linux. This is the agenda. We have 8 parts to go through. Hope we can finish in time for lunch. Traditional sampled profiling will periodically interrupts program to grab the machine status. Most CPU can do it in pure hardware, or even can emulate it in software by using some sort of timer. But modern CPUs can support more advanced hardware profiling capability. Take Intel, for example. We had PEBS, LLVM, PT processor tracing. For AMD, it had IBS, LLVM for ARM. It had SPE, BRBE, and core side. Even for RISC-V, it also had CTR, which is very similar to our LLVM. So with all these advanced hardware features, it would be possible for us to profile multiple events at one time with lower overhead and other benefits such as reduced scaling, precise distribution, or even we can sample the data linear address of each load and store instructions. So let's take the Intel PEBS for example. We see some people also call it precise event-based sampling, but the official name should be called process event-based sampling. But basically, they mean the same thing because the PEBS buffer contains multiple records which can significantly reduce the number of interruptions triggered by the performance counter overflow. So we can significantly reduce the sampling overhead to an order of magnitude reduction from traditional pure interruption-based sampling method. And as well, it can reduce the scaling or even provide precise distribution. Another example for the advanced hardware feature for profiling is Intel LLVM. The last branch recording will make CPU be able to collect data for each taken branch. To a set of hardware registers, the data sampled included the source address, the source IP, the target IP, and some meta information such as misprediction. And one thing I want to emphasize is that the LLVM can be done in parallel when CPU executing the program without any slowdown. But there will be some performance penalty when we are trying to read out this data from the hardware registers. But overall, the overhead is very small. With some reasonable sampling rate, we can keep the overhead be less than 2 or 3%. So it's acceptable for most production deployment. So with all this advanced hardware profiling knowledge, we propose the hardware-based PGO, which is an extension of existing sampling-based PGO. But for hardware PGO, essentially it's still a kind of sampling-based PGO for efficient profiling. But we emphasize on the new types of hardware feedback capabilities so that we can enable some new compiler optimizations, since modern hardware can track a wide range of events besides the traditional instruction retard. For example, we can track the branch misprediction. We can track the cache misses of both data and instruction. We can even track the cache misses, the memory access, and the data linear address of each node and store instruction. So we can do new things with all of this hardware advanced capability. So let me show you an example of such a new feedback capability. On Linux, if you run this perf command, which -b, it will capture the LBR record, and we can add some event for traditional execution frequency with precise distribution. We can even add another event for misprediction, so we can do multiple events sampling at one time. Here is the example for the collected samples. As you can see, we sample both of them. With such kind of new feedback capability, a compiler can do more optimizations. Let me show an example from a macro benchmark, and we will do a demo later on. As you can see, there is a if statement in the line 3. This if statement is in a loop. So traditionally, a compiler is very hard to predict whether it will be, how well it will be predicted at runtime. If it's predicted very well, then we can generate conditional instruction for the if statement condition. But otherwise, if it's predicted very poorly, then it would be good for us to avoid generating conditional branch. It's very hard for the static analysis to decide which solution would be better. But with hardware PGO, with the new capability we just shown you guys, we can make the reasonable decision. For example, if the hardware profiling tell us that this if statement is poorly predicted according to the events we just mentioned, then we can attach the unpredictable metadata to the branch instruction. This is existing metadata in LLVM IR. So we can add one hardware PGO optimization to transform this if statement to some straight-line statement to avoid the misprediction. And can list more assembly details here. As you can see on the left side, we have a, it's very nice. We have a very highly mispredicted conditional branch. And if we can use hardware PGO to transfer it to the right side with a number of conditional move, then we can avoid the misprediction. So we can get the overall performance statistics for this transformation. As you can see, there will be a 1.8 speed up for the runtime. And the retired branches instruction are reduced by 35%, and almost all the mispredicted instructions are gone. But meanwhile, the overall retired instructions increased about 10%, but it's still profitable. Since we improved the instruction per cycle, the IPC by 2 times. So we call such kind of optimization is related to the microarchitecture. Traditional instrumentation-based PGO cannot do it, but hardware PGO could do it. So as you can see, hardware PGO requires not only enabling more hardware features, we also needed to enable more compiler optimization. So we call the whole community to collaborate on the infrastructure improvement for more feedback capability and the compiler profiles, such as the branch misprediction, cache misses, data access in the future. And we also community to collaborate on the optimizations for such new kind of profile types. Okay, besides enabling new hardware features, we also want the hardware PGO to support more platforms. Yeah, our Intel compiler has already supported the sampling-based PGO or hardware PGO on Windows already, and we just upstream most of the changes to LLVM main branch recently. So LLVM will become the first open source compiler which can support sampling-based PGO or hardware PGO on Windows. Yeah, we are the first one to do it. No other compiler can do it today on Windows. So yeah, the first thing for supporting Windows is to enable the profiling tool. Our Intel VTune SEP has already supported some Linux perf script output format since the version 2024. As you can see, this SEP command will emit some additional text output, which is compatible with the Linux perf script output, given some extra option perf script and some parameters. And the text output format is compatible with the Linux one. At the very beginning, it has some memory map information for each executable binary, and then follows a lot of samples. For each samples, we have it event name, we have it event IP, and we also have the ARBR stack information. So the profiling tool is already done. And the second thing for Windows support is to enable the symbolization, which will turn the binary address to the symbols. So our solution is to use DOF instead of PDB on Windows. The major consideration is that we find that PDB will encode demangled or display names into the metadata, but DOF will encode mangled name or linkage names into the metadata. But the mangled name is the key thing for symbolization to associate the profile back to the compiler IR. Here are some two examples. The first one is about the inline table. Yeah, both Windows and Linux, we use it for describe the inline. We find that PDB will encode the display name into the inline table. But DOF will encode the full mangled name. And the second example is about the global function. We find that the PDB will encode the demangled name. As you can see, it actually has a qualified name, but it's not what we want. We want the mangled name, which DOF has supported. So there are also other considerations, such as the discriminate support by PDB and the start function number supported by PDB are not as good as LLVM DOF support for Windows. So since LLVM has supported DOF on Windows very well, so we just use it for the symbolization. The third one for the Windows work is to make the LLVM prof understand COF file with DOF as the simple debug information. We enhanced two major components of this tool. The first one is profile binary. We make it node and disassemble the COF file. The second one is the perf reader. We improve it to work properly with the output generated by SEP. With all of this work, we finally make the sampling-based PGO or hardware PGO work on Windows, and all of the patches have been upstreamed. Then let's do a quick demo on Windows to demonstrate all of the things I have mentioned. The demo is performed on our 12-core i7 Windows server, and I use a local client in my computer which has some sort of support for the hardware PGO, and all the changes will be upstream very soon. Firstly, let's build the baseline binary. without the hardware PGO support. And then let's build it again, but with more flags to produce good debug information. As you can see, we use DOF on Windows for the debug information. And then let's use SEP to profile the binary on Windows. The SEP version is 2024. And we use SEP to profile 2 events. The first one is about the execution frequency. The second event is for the misprediction. And we also provided the extra option for perf script output. And then we just run it with perf, with SEP. As you can see, we will get one more file besides the TB7. It's called perf data script. And the format of this file is compatible with that of Linux. At the very beginning, we have mmap information, then a lot of samples. We have samples for the branch instruction returned. We have a lot of such samples. We also have samples for the branch misprediction returned. This is the new capability we are trying to demo. Yeah, we can do 2 of them in a single run. Then we will feed back this perf data script to the LLVM gen tool to generate compiler profiles. We will generate frequency profile, which is similar as the traditional sampling-based PGO profile. As you can see, the performance counter value is associated with each relative line number by function. And we also generated the new profile type for the misprediction. And its format is very similar to the existing frequency compiled profiles. As you can see that, there are a lot of warnings. So as you can see, the relative line number 5 has a very high misprediction performance counter value, and the according source code line number should be line 24. This branch is heavily mispredicted by our CPU BPU unit. So let's feed back these 2 compiler profiles back to the client to do the hardware PGO transformation, as we just mentioned. It's very easy, just provide the profile names. Then finally, we can run the baseline binary, and the runtime is about 0.0 seconds. Then we run the hardware PGO version. As you can see, we have a speed up of 4 times in our Windows desktop. So this is a quick demo for our hardware PGO capability. And most of the patches have already been upstreamed. So there is still a lot of challenges for our hardware PGO. The first one is usability. As you can see in the demo, we just put a lot of flags into the command line to generate better debug information. But it's very hard for the ordinary users. We need some solution to simplify and consolidate these options. For Intel compiler, we put forward an option called profile sample generate, which is symmetric to the existing profile sample use. As you can see, it also would be very difficult for the LLVM prop gen and the client chain to produce, manage, and pass a lot of profile types, such as the profile for frequency, the profile for misprediction, profile for cache miss, and so on. So we are considering some profile bound solution, and we plan to post the IFC to the community very soon. So to discuss with the community. The second challenge is about the debug information accuracy. Yeah. As you know, hardware PGO use debug information to associate compiled profile data back to the compiler IR, but it suffers from the inaccuracy problem caused by the optimization. Yes, we can turn off this optimization, but it will impact the performance. We can also use the pseudo instrumentation proposed by Meta engineers, but the binary still will be a little different. We can also enhance the debug information module. For example, we just fixed one such bug in CodeGen for the indirection jump table. So we noticed there are a lot of such bugs in community. So we call the community to pay more attention to the debug information accuracy problem. The third one is profile maintenance. Actually, it's already mentioned by our first talk. Yeah, we find that there are still a lot of bugs for the profile maintenance. Some optimization changes the control flow graph, but it don't update the metadata for the profiles and the probability information. So it will hurt all kinds of PGO, including the traditional instrumentation-based PGO. So we call all the community to pay more attention to such kind of profile maintain issues. The last one is about the value profiling. Yes, the instrumentation-based PGO can do it, but the sampling-based PGO cannot do it so far. But in theory, our hardware-based PGO should do some kind of value profiling. As you can see, there is a perf record command with some special option user registers. It can collect all the general purpose register value. As you know, on x86, we use EDI to pass the first parameter value, ESI for the second one. So we should able to catch a limited number of arguments value with our hardware PGO. So we can support some sort of value profiling in hardware PGO to catch up with instrumentation-based PGO. So this is our future work. And we just list out all the patches we have submitted during the past 1 year, including the Windows support, profile maintenance, debug information fix, and split off from the COF file. And we even fixed some performance gap between the hardware PGO and the instrumentation-based PGO. So in a summary, yeah, hardware-based PGO is good for the lower overhead sampling, higher accuracy, and most importantly, it will enable new feedback capabilities provided by hardware for higher performance gains. And there is a lot of work to do for the community to collaborate on the infrastructure to support the new capability, new profile types, and add more optimization paths for these new types, and enhance the debug information, profile maintenance, and even support the value profiling in the end. So let's work together on the hardware PGO for this new stuff. That's all. It's time for questions. Thank you.
Okay, please go ahead. We have time for 1 or 2 questions.
Thanks. This is great talk. I have one question. So I think you mentioned the challenge that we saw as profile maintenance and correlation quality, but for hardware PGO specifically, some of these things, do you think it's easier to do in post-link optimizer like Bo? Because in that, you kind of cut this full cycle short, right? If you want to map the branch miss for that particular branch, you don't have to go through the full cycle. You can just pinpoint a branch in the post-link optimizers.
Just one question?
Yeah.
Okay. Actually, we also studied the board. It has some capability to do the misprediction, but as you know, it's working on the binary level. So it cannot do very aggressive optimizations. For example, if we have a function call in both sides, I think it's very hard for them to merge it into single one. But if we have a triangle-shaped branch with only one or two instructions, we can do it in both. Yeah, that's right. But the compiler can do more aggressive optimizations. Yeah, I can show you a more complicated example we find in the real benchmark Comarch Pro. As you can see in the left side, we find that this branch is highly predicted by our hardware. But the complexity, the challenging thing for this if statement is you can see there is divide operation in both sides. If we want to do it speculatively, we need to consider the corner case. If the dividend is zero, how can we do it equivalently? Yeah, I think it's very hard for both to do many complicated things. But yeah, they can do it for some sort of hardware PGO. Either, yeah, that's right.
Thanks.
One more question.
One quick thing to mention is that for value profiling, we also have some prototype that's developed in-house, so maybe we can collaborate on that. It's exactly the thing that you mentioned, how to use PEPs to get value for the parameters.
Sounds great for follow-up discussions. Let's do one more question. Yeah, take it.
Thank you, Wei, for the talk. Very interesting. I have one comment and one question. The comment is, I'm not sure how closely you're working with architects on defining the features for the new generations of processors, but considering what have been presented previously, specifically CSS PGO, which makes use of both LBR for branches and call stack profiling, it would be nice to have the capability to sample both at the same time. And I'm not talking about the programmable LBR feature where you can select multiple events, because the two kinds of events would consume limited buffer space, whereas CSS PGO requires both at the same time. So it would be nice to have a sample of return stack buffer included in the LBR sample. So that's the comment. And one question is, what is the architectural LBR insert? Can you please explain what's that?
Oh, okay. So maybe I can go back to the slide. So, okay. Sorry. Oh, what happened? So I think your question is about what is LBR insert, right? Yeah, the problem with the current LBR hardware feature for Intel processor is that we just have it for PGO, the core for server, but we don't have it for small core, such as Atom. So we want to define a architectural event for both PGO and eco in the future for every generation of Intel new hardware in the future. So we call it LBR insert. Yeah, it will be available in the upcoming process very soon. Yeah.
All right, I guess we have to thank the speaker. You're over time, so thank you, Wei, for your talk.
Thank you.